In this video, we present goal representations for instruction following. Past work on learning instruction following policies has struggled to succeed in real-world robot settings. On the left, the BCZ baseline fails to correctly ground its instruction as it moves to the wrong target. On the right, the baseline fails to robustly generalize a manipulation skill to a new instruction. We propose our approach, goal representations for instruction following, or GRIF, to improve this performance in semi-supervised settings where only a portion of the trajectories are annotated with language. Our key insight is to use a contrastive objective to align task representations of language and image goals that can then be used to condition the policy. We test our approach in a tabletop manipulation setting with a WidowX arm. The robot policy receives instructions L and observes states through the side camera to select gripper actions. Learning to follow such language instructions conventionally requires large amounts of labeled robot data, which can be hard to get. Instead, we seek to ground language instructions using pre-trained vision language representations with large amounts of unlabeled robot data and only a small number of trajectories with language labels. Our approach thus provides a scalable system that can train on plentiful unlabeled robot data, perhaps even data that is collected autonomously, and then use this experience to improve its ability to follow language instructions. Here's an example of how our approach executes a language instruction in this scene. The robot gets the instruction, put the pan on the towel. We convert the instruction into a task representation Z. From this representation, the policy can select an action A. However, we only have a small amount of supervision for this language-conditioned action selection since most of our data is unlabeled. We improve the policy performance by additionally supervising the action selection with tasks representing visual start-goal transitions in the scene. Since we can hindsight relabel any trajectory with its start and goal, we can now use all unlabeled robot trajectories, including those that are autonomously gathered. This additional supervision greatly improves robustness, allowing us to complete the task. Let's go through our training process. We start with a small set of language-labeled trajectories annotated by humans. We can generate task representation Z from these language labels and learn a policy on top of these tasks with behavioral cloning. We have a much larger set of unlabeled trajectories from which we can relabel end states as goals. We additionally learn task representations from these goals that represent the change from the start. We use behavioral cloning on these tasks to tune the policy further. To ensure knowledge from unlabeled trajectories transfers to the language condition policy, we additionally use a contrastive objective to align language task representations with goal representations on labeled trajectories. Here are some examples of our GRIF approach, grounding and executing diverse instructions from the same initial scene. We can put the pan on the towel. We can put the pepper in the pan. We move the bell pepper to the left of the table. And we put the yellow bell pepper on the cloth. In summary, our approach is able to train on language annotated and goal relabeled trajectories. Contrastive task alignment enables robust grounding and transfer. We then show this approach outperforms baselines on unseen instructions across scenes.